Welcome to this video on the topic of forces and elasticity. Before looking at elasticity, let's remind ourselves about the effects that forces can have on an object. If there's just one force acting on an object, it can cause it to slow down, speed up, or change direction. A force can also cause an object to rotate in some way. Things get a little more interesting when more than one force acts on an object. When we stretch or extend an object, tension forces will try and pull it back to its original shape. Likewise, when we squash or compress an object, compression forces will try and push it back out to its original shape. Finally, forces may combine so as to bend an object, as shown here. This is what happens on a very small scale every time a car crosses a bridge, for example. When forces change the shape or the form of an object, we say that the object has been deformed. These deformations can be either elastic or inelastic. As you can see from these definitions, when an object is deformed elastically, it will return to its original shape when the forces acting on it are removed, but an object which has been deformed inelastically won't. For your exam, you'll need to know how the force exerted on an object changes as we stretch or squash it, and the most likely object which you'll be questioned on is a spring which looks like this. This spring is attached to a support at the top and is allowed to hang down freely. You won't be surprised that when we attach a mass to the spring, its weight causes the spring to stretch downwards. The total change in the spring's length is called its extension. We say that we have extended the spring by applying a force to it. If we carry out an experiment in which we apply lots of different forces to the spring and measure its extension each time, we end up with a force extension graph which looks like this. As you can see, the relationship between E and F is linear here, which is another way of saying that E is directly proportional to F. As we double F, E doubles, and so on. Some of you may recognize this relationship as Hooke's law, but you don't need to remember this term for your exam. Many, but not all, springs behave like this when the force applied isn't too large. This relationship is summed up by the equation F equals KE, where F stands for the force in newtons, E is the extension in meters, and K finally stands for something called the spring constant, which is measured in newtons per meter. That all might seem a bit too perfect, and the troublemakers among you might be wondering what happens if we keep adding more masses to the spring. Beyond a certain point, which is called the limit of proportionality, our nice graph will stop being a straight line. Because of this, we can say that this part of the graph is non-linear. Just one last thing before we move on to a few examples. A spring which isn't overstretched will always go back to its original shape, so a spring which is stretched, say, this far, is only elastically deformed. When a spring is stretched beyond a critical point, however, which we call its elastic limit, it will never return to its original shape, even if all the masses which had been added to it are taken away. Let's move on now to a couple of examples in using F equals KE. As you can see here, the spring constant is 20 newtons per meter, and the spring has been stretched by 10 centimeters, so let's give it a quick go. The only real point in this example is that the spring extension must be given in meters, so we'll convert 10 centimeters to 0.1 meters. After that, this is a very straightforward pure substitution question, so F equals KE gives 20 times 0.1 to give a force of 2 newtons. Our second example here is just a touch more complicated. Again, starting by highlighting the key information, the mass is 600 grams. The spring constant this time is 50 newtons per meter, and we've been given a value for G, the gravitational field strength, of 10 newtons per kilogram. So how do we go forward? To start this one off, we remember from our gravity video that the weight exerted due to the mass is given by W equals mg. Converting the mass into kilograms, that gives 0.6 times 10, which gives a weight of 6 newtons. If we then think about our equation F equals KE, We've just worked out that the force pulling the spring down has a value of 6 newtons. In the question we've been told that K equals 50 newtons per meter. So to work out E, we just have to rearrange the equation to give E equals F divided by K, which gives 6 divided by 50, which gives an extension of 0.12 meters or 12 centimeters. Have a look at this example now. As you can see, in part A, we need to work out the spring constant of the spring used, so let's get to it. The first thing to do here is to plot a best fit line through the points, which will look something like this. Next, we again use the equation F equals K times E, which we rearrange to give K equals F divided by E. What we then do is pick any point on this straight section of graph, such as this one, and read off the values for F and E, and then sub them into our equation. So that gives 10 newtons divided by 1 meter to give a final answer of 10 newtons per meter. For part B, we can see that the new spring has a spring constant which is half that of the first one. To sketch this graph, we're going to need 2 points. The first of these is easy to get. When the applied force is 0, the extension of the spring is 0. When you don't add anything to the spring, it doesn't stretch. For the second point, it's going to be a quick calculation. We know that K for this spring has a value of 5 newtons per meter. What we're going to do next is to pick any value of F above 0, like this one, and then rearrange our equation to work out what the extension is going to be at this force. Subbing in, that becomes 4 divided by 5 to give an answer of 0.8 meters. What we do then is we plot our point on the graph for 0.8, and then we draw a line between these 2 points for our sketch graph, another full marker in the bag. Have a look at this example next. We again begin by drawing a best fit line through the points, which is going to look something like this. For part A, we rearrange F equals KE to give K equals F divided by E, and then sub in any 2 values from the graph. I'm going to pick the top point, which is going to give 12 newtons divided by 0.3 meters to give a final answer of 40 newtons per meter. For part B, we've been told that the limit of proportionality for the spring is at an extension of 30 centimeters, and beyond this value, the stiffness of the spring begins to decrease. Remember that something which is less stiff is easier to stretch. For every extra newton of weight that we add to the spring beyond 12 newtons, its change in extension will become larger and larger, which means that the graph will curve upwards like this. This is just a very quick section of the video to show you that everything we've covered so far applies to a spring which has been compressed as well. The only difference is that in the equation F equals KE, E stands for the compression of the spring, or how much it's been compressed by in meters. Let's look at this example to show you how straightforward this is. As you can see here, the spring constant is 75 newtons per meter, and a force of 15 newtons is applied to this spring. To work out the compression, we just rearrange F equals KE to give E equals F over K, and subbing in, that gives 15 divided by 75, which gives an answer of 0.2 meters. In the required practical for this part of the course, you have to investigate the relationship between the force applied to a spring and its extension. I know you really love doing lots of physics, so the good news is that we've basically covered this part of the course already, but just to make sure you don't get any surprises in the exam, we'll go through the experiment itself in full detail here. The setup you're most likely to use for this experiment looks like this. As you can see, we're using a retort stand and 2 clamps to place a meter stick alongside a spring which is hanging vertically. To prevent the apparatus from toppling over, the retort stand should be clamped to the desk. As an additional safety precaution, you should wear safety glasses when performing this experiment in case the spring is accidentally catapulted towards you. We start by measuring the position of the bottom of the spring on the meter ruler. Of course, the ruler has to be quite close to the spring for this measurement to be carried out accurately. We then attach a 100 gram mass to the spring and measure the new position of the bottom of the spring. The extension is of course just equal to the difference between this and the original position. We then repeat this for additional masses. Typical results from this experiment might look something like this. To calculate the force exerted in the spring for each mass, you just use W equals mg. In other words, you multiply each mass in kilograms by the gravitational field strength. We need to be careful here in calculating the extension. The first row of data shows us the position of the bottom of the spring when no force was applied to it, so the extension at this point is 0. As you can see, when a 100 gram mass was added to the spring, the bottom of the spring moved down to a position of 51.7 centimeters, so the extension at this point was 51.7 minus 50, which gives a value of 1.7 centimeters. In each case then, the extension is just equal to the difference between the current position of the bottom of the spring and its original position of 50 centimeters when no force was applied to it. By carrying on in this way, we end up with a full set of results. The independent variable here is the force, and the dependent variable, the variable that was affected by changing the independent variable, is the extension. This means that a graph of our results should have the force on the x-axis and the extension on the y-axis like this. When we draw a best fit line for this graph, we see that it's a straight line through the origin. The extension of this spring is proportional to the applied force. Its limit of proportionality hasn't yet been reached. The next section of the video may look familiar if you've already learnt about types of energy. When the shape of an object is changed, we say that work is done on it, which means that energy has been transferred to it. If the object has been deformed elastically, the amount of work done on it will be equal to the amount of elastic potential energy which has been stored in it as a result of its change in shape. If the object has been deformed inelastically, some of the energy which has been put into changing its shape will be used in reorganizing the particles inside it, so that it won't return to its original shape if the force is removed. And if this all sounds a bit dry to you, remember that without this stored elastic potential energy, you wouldn't be able to flick an elastic band, jump on a trampoline, or do loads of other pretty cool stuff. Let's go back now to our good old spring. If the force applied to the spring is proportional to its extension, then the amount of elastic potential energy stored in it is given by this equation. Here, EE stands for the amount of stored elastic potential energy. And as with all energies, of course, this is measured in joules. K, as previously, stands for the spring constant, which is measured in newtons per meter. And E stands for the extension or the compression of the spring, which is measured in meters, of course. Have a look now at this quick example. Starting off as always by highlighting the key information in the question, we see that K equals 5 newtons per meter here and E equals 0.3 meters, so let's get started. Hopefully you'll see that this is a straight substitution question, so using the equation we have EE equals a half KE squared, and subbing in, that gives a half times 5 times 0.3 squared, which gives an answer of 0.225 joules. On now to one last example for this video, and as you can see the spring starts off at 10 centimeters long, but when a 4 Newton weight is added, it extends to a total length of 15 centimeters. As you can see, that just means that the extension of the spring, which is marked here, is 5 centimeters in total. To work out the value of K, we just rearrange F equals K over E to give K equals F divided by E, subbing in our numbers then 4 newtons, converting the extension into meters as always to give 0.05. That gives a spring constant of 80 newtons per meter. Down to part B now, and as you can see 10 joules of elastic potential energy is stored in the spring, and we've been asked to calculate E, the extension, so let's go. As previously, starting off with the equation for elastic potential energy, which is EE equals a half KE squared, subbing in the numbers which we have, 10 joules equals a half times 80, which is our spring constant, times E squared. Our next line then would read 10 equals 40 E squared. So dividing 10 by 40, that shows us that E squared is 0.25, and taking the square root, E is just 0.5 meters or 50 centimeters. The only tricky thing then about part C is to make sure that you realise that the weight is just the force which is being applied to the spring. So using our previous equation, F equals KE, and subbing in, that gives 80 times 0.5, which gives an answer of 40 newtons. Phew, I'm tired after all those calculations. We've managed to compress a lot into this video. Hopefully you didn't find it too stretching. Physics puns aside, this topic really should make for easy marks in the exam, so make sure you don't end up getting caught out by testing your understanding with a few of the exam style questions. Good luck.